So the secret to which of those cations wins the electrons lies in the analysis of something we have already done before, and that is to ask the question, do all metals react in an ionic solution? So let's take a look first at the left-hand beaker. The left-hand beaker has pure copper inserted into a solution that contains silver cations in aqueous solution. But by inspection we can see a reaction has taken place because the blue color that's intrinsic to the solution represents the presence of copper 2+ aqueous cations. But more than that, when we look, we see pure silver, solid silver, plating out on that copper. By direct deduction through observation, we know that pure copper solid has gone to the blue copper cation in aqueous solution, which liberates 2 electrons. At the same time, if we have formed silver, pure silver, as a product on the right-hand side, so we have pure silver solid, then we know that we had to convert silver cations in aqueous solution with an electron to produce that pure silver. That takes us back to our favorite diagram, which is the Gibbs free energy diagram. And so let's look at what the observations told us, looking at the beaker in terms of that Gibbs free energy surface. So we started with pure copper. The copper cations went into solution, that's the blue color. The silver cations in solution came out of solution and plated out on that pure copper slip. So if we draw the Gibbs free energy diagram for that, we have the reaction of pure copper with silver cations, and we have to balance the equation because it takes 2 electrons, producing the copper cation and the pure silver. And that means that those reactants were connected to the products on a Gibbs free energy surface by those electrons rolling down the hill toward the products. And as we know so well, that means that the change in Gibbs free energy for that reaction is less than 0. So it's spontaneous. If we investigate the right-hand beaker, again we start with pure copper, but in this case, in this solution we have zinc cations, aqueous, and we see that no reaction occurs. And that means that if I write copper solid going to copper 2+ aqueous plus 2 electrons, I know that that reaction hasn't taken place because there's no blue color in the solution. And more than that, the zinc 2+ aqueous has not reacted with 2 electrons to produce the zinc solid because there's no zinc solid deposited on the copper electrode. So I know that that reaction is non-spontaneous. So if I write copper going to copper 2+ with zinc 2+ going to zinc metal, those 2 electrons have to flow uphill on a Gibbs free energy surface, and that means that delta G must be greater than 0, and that reaction is non-spontaneous. But therein lies the hint, because if I turn that reaction around and I react copper 2+ with electrons, then I will form pure copper, and the zinc solid will go to the zinc cation, and those electrons will flow downhill. Therein lies the secret to which cation in our original combination of reduction oxidation beakers won that tug-of-war to attract electrons to it. So let's see what that looks like when we plot it out on a diagram.